Hello everyone, welcome to the Stats Workshop. Right now we are going to be going over ANOVA and multiple comparison techniques. So without further ado, let's jump right into it. Now in the first part of the workshop, we went over how to do the two-sample t-test and how it can be used to compare between two treatment groups, say a control and a drug treatment. But what are we going to do when we have more than one treatment group? For example, perhaps we have a control group, a group that was given a half dose of a drug, and a group that was given a full dose. How do we determine if any of these groups are significantly different from each other? While we are thinking about this problem, I would like to note that we cannot just do multiple t-tests. I'm going to explain a little bit more on why this is later, but for now, just trust me, it's a bad idea. Now, the correct solution to this problem is ANOVA. ANOVA stands for Analysis of Variance, and it can be used to conduct a statistical test no matter how many different treatment groups you are looking at. In ANOVA, your null hypothesis is always that all of the groups have the exact same mean value for our variable of interest. Your alternative hypothesis is that at least one of the treatment groups has a significantly different mean. Now note that ANOVA does not show us which groups are different from each other, so it does not tell us which of these situations is true or the most likely. It just tells us that at least one group is significantly different from the rest. This is very important to remember, and it is the reason that people rarely do just an ANOVA test when they are conducting an experiment. Now, the idea behind ANOVA is that we are asking ourselves, how much variation do we expect to see between the groups due to sampling variation? So, how reasonable is it that all of the variation we are seeing comes from random chance? Well, if there are no differences between the groups, then taking a random sample from each group is the same as taking a random sample from one big group. All the populations are identical under the null, so picking between multiple populations does not mean anything. This means that while doing ANOVA, we can treat all of the data points from the different groups as one big sample, and then analyze the variation within that one big sample. If there is more variation in that sample than we would expect, assuming the null is true and the populations are the same, then we can conclude that at least one of the groups is actually different, which is the source of the extra variation. I really hope that made sense, but even if it did, it is probably hard for all of you to imagine how you can actually analyze these sources of variation practically. Now, in practice, doing ANOVA manually is a truly painful experience. There are at least 8 different values you need to calculate. It takes forever, and it's basically never done. Everyone just does ANOVA in R, or some other kind of coding language. So we are just going to jump straight into R now and give ANOVA a try. So all of you should be going into your Stats Workshop folders, going into ANOVA work, and opening up the ANOVA script working RMD file. I'll see all of you in R. Alright, so we are in our ANOVA script working.rmd file, and the first thing we are going to do is we are going to load up the dplyr package. So to do this, please run install.packages dplyr if dplyr is not already installed on your computer, and then we're going to run library dplyr to load it up into our R session. Then the first thing we're going to do is generate some data. This should be familiar to you at this point. We're going to generate up 3 different samples using 3 different calls to the rnorm function, and these are going to represent samples from 3 different populations. So use a sample size of 20 for all the samples, set the mean of the first 2 samples as 2, and then set the mean of the last sample as 4, Then we're going to use a standard deviation of 1.5 for all samples, and we're just going to call them x1, x2, and x3. Then once you've made that, you should look at them using the box plot function. Now, we have to actually organize our data this time around because the ANOVA function is a little bit different and it likes to work with data that has been organized in a certain way. So the first thing we're going to do is bind all of our samples together using cbind. Then we are going to reorganize them using the stack function. And then finally, we're going to use dplyr as rename function to change the column names from ind to group, which is just going to be a lot more intuitive moving on down the line. And then once you have completed all of these manipulations, our data is all set for running an ANOVA test. Now, when it comes to ANOVA, we're going to learn it in a way that is kind of backwards from how we've been doing it before. We are going to start by actually conducting an ANOVA test, and then we are going to use R to explore what all of the different outputs of the test mean. So then in order to run an ANOVA test, we are going to need to use R's linear regression function, which is called LM. Now, why are we using linear regression for ANOVA? Well, it's because ANOVA is actually a special application of linear regression. We may explore this more in future workshops, but for now, do not worry about it. So to start off, run the help function and focus on the first two arguments. I'm actually going to do that right now. So I've run this, I have fitting linear models brought up, and looking at the first two arguments, the first thing that is going to come up is that you need an object of class formula. Now, what is a formula class object? Well, formula class objects are specified using a tilde, which is this sort of little wave mark you see here. And we are going to use it to specify a relationship between two vectors. Essentially, if you type A tilde B, you are saying that you want to test if variable A is dependent on B. The first term is the response variable in your data, and the second is the explanatory variable. Now, for the more computationally inclined people here, you might be thinking that that doesn't really describe what a formula object actually is in R, but the specifics of that are complicated and beyond this workshop. If you want more details, I suggest you look up formula after the workshop is completed. Okay, but now that we understand how the LM function works, we can actually run some ANOVA. So we are going to create an ANOVA object using the LM function, and then we are going to use the ANOVA function on that AV object we just created to actually run the ANOVA test. The output of this test should look like a table, and once you're all done, we're actually going to hop over to the slides so we can look at this output table more closely. All right. Let's look at the ANOVA table without all of the abbreviations found in R. You can see that vertically we have group and residuals. For the rest of this lesson, I will refer to residuals as error as a matter of preference. Then horizontally, we have degrees of freedom, sum of squares, mean square, the F value, and the P value. The reason the table is set up this way is so that you can do something like go to group, go to mean square, and then go down to mean square group. Now, the F value and the P value, they don't really work like this. They're just sort of on the side here doing their own thing. And on a side note, you'll notice that there's another row here called total, and this is just equal to the group plus the residuals. It's not super important, but you're going to see it come up sometimes when people show these tables, so I don't want anyone to be confused. Now, moving on, we are going to describe what each of these different things in the table actually mean. Let's start by talking about the sum of squares. Sum of squares is a measure of the variation in our sample, with sum of squares total being the total variation, sum of squares group being the variation between groups, and sum of squares error being the variation within groups. I believe that the best way to explain these definitions is with a kind of graph. In each of these graphs, we see three different groups: a red group, a blue group, and a yellow group. Then we also see a large black line, which is the grand mean, which is the mean of all of these points, and we can see some orange lines, which represent the means of each individual group. The first graph shows the total variation. If we added up all of these black lines, all of these deviations from the grand mean, we would get the total sum of squares. Now this total sum of squares can be split up into the group sum of squares and the error sum of squares. So if we added up all of the distances between the group means and the grand mean, we get the group sum of squares. If we added up all of the distances between each individual point and their individual group mean, then we would get the error sum of squares. I am hoping that you now have an intuitive sense of what I mean when I say the between group variation and the within group variation. Now let's move on to degrees of freedom and mean square. So we've talked about degrees of freedom before, but we've kept it very simple, and we're going to keep it simple. For now, all you need to know is that they are related to the sample size. When it comes to the group degrees of freedom, sample size refers to the number of groups. So degrees of freedom is number of groups minus 1. When it comes to the error degrees of freedom, sample size refers to every individual sample replicate and is equal to the total number of data points minus the number of groups, or n minus k. Moving on, mean square is equal to the sum of squares divided by the degrees of freedom. Now, what dividing by the degrees of freedom does is make it so that the mean square error and the mean square group can be thought of as having the same units. We are now looking at the mean variation per individual for the between group variation and within group variation. The fact that mean square group and mean square error are comparable and have the same units is important for the next value we are going to calculate. So the most important output of the ANOVA table is the F statistic. It is sort of the equivalent of the T statistic for ANOVA. The F statistic is equal to the mean square group divided by the mean square error. Now, let's think about this. If the null is true and there are no differences between the groups, then we would expect the variation between groups to be roughly equal to the variation within groups, because there is no extra variation happening between the groups. This means that if the null is true, the F statistic should be equal to around 1. Now, if the null is false and there is a difference between the groups, then we would expect there to be extra variation between the groups because the groups are systematically different. This means that if the null is false, then the F statistic should be greater than 1. Now the only question that remains is how much greater than 1 does F need to be for us to conclude that one of the group means is significantly different. We're going to hop back over to R now and figure out how we actually determine this. Alright, so what we're going to do with this chunk of code is that we are going to create an F distribution that will allow us to calculate p-values from our F statistic. This is going to be pretty much exactly like what we did with the T statistic and the T distribution. So we're going to create the F distribution using the df function. This is going to function a lot like the dt function that we used to create the T distribution, but it's going to have two different inputs for the degrees of freedom. df1 is going to be the group degrees of freedom, and then df2 is going to be the error degrees of freedom. So, after you have plotted your F distribution and you have added a rejection region to it using this code here, you should end up with something that looks just like this, where we have our distribution, then we have our red rejection region where the area to the right of this line and underneath this curve is equal to 5% probability. And now we just have to see if our F statistic lands somewhere in this region. If it does, then we can say that there is enough evidence to reject the null hypothesis and that p is less than 0.05. We can say that we are confident that at least one of the means is different from the rest. All right, now let's head back to the slides. Okay, so we are done learning about ANOVA now. Let's all take a big breath and go over some assumptions. We are assuming random sampling, of course. Basically, all classical statistics assumes random sampling. We are also assuming that the variable of interest is normally distributed in the population of every group. And just like the t-test, ANOVA is robust to this if the sample size is large due to the central limit theorem. Finally, just like the two-sample t-test, we are assuming that the variance of the variable of interest is the same in the population of every group. Now, for those of you who have been thinking critically about what I am saying, you probably realize that there is an inherent problem with ANOVA. ANOVA can only tell us if at least one group is different, but usually we want to actually know which group is different. For this reason, ANOVA is often insufficient to actually answer any of the questions we pose in our projects. So why do we even do it, and why do all stats courses teach it? Well, remember, ANOVA is the analysis of variance, and it allows us to actually quantify how much variation is caused by changing our variable of interest. This is a great way for us to get a feel and an understanding for how some treatment or variable is affecting our study group. This importance of ANOVA's ability to analyze sources of variation is even more apparent when we look at the other kinds of ANOVA. Random effect ANOVA allows us to determine the amount of variation that is being added to our experiment by random factors. For example, you can use it to determine how much variation is being caused by sampling error. Two-way ANOVA is even more cool because we can use it to look at how much variation was contributed by different variables, and it even lets us see how much variation is caused by the interaction between variables. We unfortunately do not have time today to go into the details of how these kinds of ANOVA tests are run, but the message I want you to take out of this is that ANOVA is not just used for hypothesis testing. Alright, moving on now. So what do we do if we need to know which groups are significantly different from each other? For example, what if we want to know if the half dose of our drug is sufficient to have some kind of effect? Or what if we want to know if the full dose of our drug is more effective than the half dose? Or if we need to know if only the full dose is effective? How do we actually determine these things? Well, the first thing that comes to mind is why not just do multiple tests? Well, remember that by setting our alpha value to 0.05, we are saying that 5% of the time, when we conduct a t-test, we will make a type 1 error, meaning that we will reject the null hypothesis when the null is actually true. So if you try to do multiple tests, then every time you do that, there is a 5% chance you make a type 1 error. So the more tests we do, the more likely it is that we will make at least one type 1 error. This is called the multiple comparison problem. Luckily for us, statisticians have developed many different methods of addressing this problem, which are collectively called multiple comparison methods. These multiple comparison methods attempt to solve this problem by attempting to control certain error rates. Some of the error controlling methods we are going to look at attempt to control something called the family-wise error rate. The family-wise error rate is defined as the probability that out of all the tests we perform, a type 1 error occurs at least once. As an example, let's say you run 102 sample t-tests. For all of these tests, the samples we are analyzing are from identical populations. So the null is always true. Now we are going to set our alpha as 0.05. With that alpha, we would expect around 5 type 1 errors to occur, because our type 1 error rate is 5% and we are doing 100 tests. But what are the chances that a type 1 error never occurs with this error rate? Well, for each test, the probability of a type 1 error not occurring is 95%. So to get the probability of a type 1 error never occurring, we just take 0.95 to the power of 100 tests, and we get something around 0.004. Oh dear, so now we know that the chance of a type 1 error not occurring is really very small. If we just look at the inverse of this probability, we get the chance that one or more type 1 errors occur. And we see that it is almost guaranteed that it will happen at least once, 99.6% chance. So our family-wise error rate is really high. Now our FWER controlling methods now attempt to reduce this value, this near 100% certainty, all the way down to a more reasonable level, such as 0.05. Now we're going to look at an example of one of these FWER controlling methods in R. So before we go into FWER controlling methods in R, I want to talk a little bit about how multiple comparison methods are done in R just in general. So most multiple comparisons in R utilize a function called pairwise.t.test. This function is used to perform multiple two-sample t-tests between all of the different sample groups. So it does that thing I told you to never ever do. But luckily it has an option to adjust the p-values of these t-tests based on different multiple comparison methods. So now, for educational purposes, we're going to run a pairwise t-test with no p-value adjustments whatsoever, just so we can compare it to our adjusted values later on. Then, after you have completed that, we're going to move on to controlling FWER with the Bonferroni method. Now, the Bonferroni method is probably the simplest multiple comparison technique in existence. In a nutshell, the Bonferroni method is just done by taking the alpha value we are using, usually 0.05, and then dividing it by the number of tests we are doing. This means that it gets harder and harder to find significant results as the number of tests we are doing increases. So, please just perform a pairwise t-test using the Bonferroni method, and then as you're analyzing the results, you will probably be able to notice what has happened to our p-values versus when we didn't make any adjustment. They have been multiplied by the number of tests you did, in this case 3. This should probably give you the idea of how if you keep doing it more and more, as these p-values are multiplied, they get closer and closer to no longer being significant. So now let's look at what is actually happening when we make a Bonferroni adjustment. We are going to see what's happening to the rejection region of our t-distribution when we conduct 50 separate tests. It's all of which are going to have a sample size of 20. So, create a t-distribution just like you've done several times before, and then add these adjusted rejection regions and also an ab line, and so you can actually see how this rejection region has changed. And you should get something that looks like this. Now, look how far off to the right this rejection region is. You can barely even see it. It's why I had us add the line. Just by looking at this, you probably get a sense for the fact that if you want to detect any significant results once you start doing something like 50 tests, you are going to need either a lot of power or a very, very strong effect in order to find anything. So what are we going to do if we need more power for our experiment? Well, let's go back to the slides so we can discuss how we can control error rates without sacrificing as much power. So family-wise error rate is pretty self-explanatory, but false discovery rate is a bit more confusing. Let's go over an example of what false discovery rate really means. Let's say you conduct 100 two-sample t-tests. Again, of those 100 tests, 90 of them are comparing samples from two truly identical populations. The other 10 tests are comparing samples from truly different populations. So you conduct the test and you find a significant difference between the sample means 15 times. So you reject the null 15 times. But wait, what happened? We know that we only should have rejected the null 10 times. The null is only truly false for 10 of these tests. The other 5 times we rejected the null must have been a mistake. It must have been a type 1 error. So 1/3 of the times you discovered a significant effect, there actually wasn't any. This is bad. FDR controlling methods attempt to reduce this false discovery rate to a more reasonable level, often about 0.05. So now we are going to jump into R once more, and we are going to look at an example of how we can control false discovery rates. All right, so the false discovery rate controlling method that we are going to be demonstrating today is called the Benjamini Hochberg method. Now, the Benjamini Hochberg method is more of an algorithm than an equation. We are going to use tables to visualize how this method decides which p-values are going to stay significant and which we are going to decide are no longer significant. So the first step to doing this is to just create a vector of p-values that we're just going to kind of make up. And this is just an example of what we could get after performing 10 tests. Then we are going to sort those values using the sort function from smallest p-values to largest. Then we are going to create a rank for each of those p-values, ranked 1 to 10, smallest to largest, and bind them together into a data frame. Now, this last step we're going to do is the most important one. We are going to compare our ordered p-values to a set of BH critical values, or Benjamini Hochberg critical values. These values are calculated as I divided by m times q, where I is the rank of the tests, m is the total number of tests that were performed, and q equals the false discovery rate we are aiming for. So in this case, we're going to do 0.05. So we're going to add these critical values to our table, and it should come out looking like this. Now, here is how this table kind of works. We look at our p-value, and then we compare it to the critical value, and we ask, is this p-value less than the critical value? So, yes, yes, yes. And then once we reach 4, it's no. All of a sudden, our p-value is higher than our critical value. So now every single value below this one, every single higher p-value, we are going to decide is not significant. Notice that this includes 4 and 5, rows 4 and 5, where even though their p-value is below 0.05, we are going to decide that these as well are no longer significant. So this is how the Benjamini Hochberg method decides which p-values are and are not significant. So now that we know that, let's just get R to do all of this for us. So please perform another pairwise t-test, this time using the Benjamini Hochberg adjustment. Then right after that, I want you to do the Bonferroni adjustment one more time, and I want you to compare the outputs from the two adjustments, Benjamini Hochberg to Bonferroni. What you should notice is that the Benjamini Hochberg adjusted p-values are a bit smaller than the Bonferroni adjusted p-values. And that is because, generally speaking, adjustment methods that try to adjust the false discovery rate are less conservative than methods that attempt to adjust the family-wise error rate. Let's head back to the slides now and just kind of wrap things up. So, now that we know of a couple of different methods, how do we choose between them? The bottom line is that choosing which multiple comparison method to use is entirely dependent on the goals of your project. If the conclusions of your paper will have immediate, important, and practical consequences, then you should probably try to be as conservative as possible. For example, if you are working on a new medical treatment, then you do not want to make any type 1 errors at all. You need to be very sure that your treatment has a real effect. These are the situations where you should use family-wise error controlling methods, such as the Bonferroni method. On the other hand, if your experiment is more exploratory, and your results will be more focused on informing future projects, then you probably want something with a bit more power to actually detect differences. For example, you might be looking at the effects that many different genes have on a certain trait. These are the situations where you want to use false discovery rate controlling methods, such as the Benjamini Hochberg method. Now, one last note I would like to leave you on is that there are a lot of different multiple comparison methods that we did not get to cover today. So if you are not sure if the methods we covered today sound right for your project, I implore you to look into some other methods to find out if there is something that better suits your needs. Alright, that will be all for today. All of the materials for this workshop can be found in a link in the description, and I hope that this workshop has given you a better understanding of how to deal with multiple comparisons, and I wish you all the best of luck in your future research endeavors.